Share control screen. Start broadcast. Okay. Okay. So okay, so I will actually start. So just recall. So what we did last proposition last class, right? So this is lecture 14, 13, 14. 14. Yeah. So just complete this. Just state it and move on. So suppose rho belongs to D of H, 0 less than lambda less than I. Trace of rho lambda is greater than equal to 1 minus epsilon. Then root lambda rho root lambda divided by trace lambda rho minus rho is at most 2 root epsilon. Okay, so we will now get into quantum entropy. Okay, so quantum entropy. I think this is chapter 13, chapter 11, but I will be doing it slightly differently from what is there. We'll be doing what we require. Okay, so recall. So for a distribution Px, it's a distribution on a finite set X, we defined the Shannon entropy, right? So H of Px is essentially minus Px of X log Px of X. So we generally use one convention, 0 log 0 is 0. The convention we use. Okay, so yeah, that is one way, but sometimes you will get that in your expressions. So we just use this. That's another way. Just remove all those that are 0. Okay, so I will state the definition for the von Neumann entropy, and then we prove properties. Okay, so definition: the von Neumann. I don't know whether it is NEU or NUE. I think it is NUE. NEU maybe. NEU, right? NEU. Entropy of a. Sorry. Oh, MANN, is it? ANN. Entropy of a density operator rho is defined as, so I'm going to use S. I don't know what will does. I think will uses S itself. So S of rho is defined as minus trace of rho log rho. Okay, recall. So for T, which is a Hermitian self-adjoint operator, and F from R to R, F of T is summation F of lambda I EI, where T has a spectral decomposition. T equal to summation lambda I EI. Right? Just recall. Okay. So let's kind of understand this. So suppose, so just the first remark 2, definition 1. So remark 2. So suppose rho is summation lambda I xi, then Then we have, and also I'll assume that the support I have eliminated those lambdas which are 0. So I'm only looking at the support of rho. Then I have log rho to be log lambda j xj xj j. So this implies that rho log rho is essentially I j lambda I log lambda j x I j j. So because this is spectral decomposition, I can write this as I lambda I log lambda I xi xi. Is okay. So S of rho is essentially minus, yeah. Say that again. So you're saying okay, so you're saying right there x log okay, yeah, okay, fine, yeah, sure. So say f of x minus x log x. So this will be minus lambda I log lambda I. So this is the Shannon entropy of the vector of the eigenvalues of the density operator. Okay, so that's remark 1. So the one Newman entropy of rho is equal to the Shannon entropy of its eigenvalues. So what does this tell us? So suppose rho belongs to D of H, and the dimension of the space in which it lives is say D. What can you say about S of rho?
It's at most D.
At most D or what? Log D.
Oh, log D.
Yeah. So at most log D and at least 0. Okay. How do you show this? I mean, just for so how do you show? Suppose Px is a distribution on X and cardinality of X equal to D. How do you show that the entropy of Px is at most log D? Okay. Yeah. Okay. Yeah, I think you can do log D minus h of Px, I think is greater than or equal to 0. You have to show, right? I think you can use it in the homework. Okay, great. Yeah, it was planned so that this will come. Okay, all this is fine. So we'll prove some. Okay, before I go there, right, I'm going to give one interesting thing. See, remember, it's actually very interesting. So remember, if you have a set X and you have Px, then you can compress it down to its entropy, right? You can compress down to entropy, right? But for this, you have to wait for a long time. You have to wait for the source to compress down to entropy. You have to wait for the source to accumulate till n symbols. Then you have to do a lot of indexing, and that guy has to do a re-indexing, right? Can I do symbol by symbol? Okay. So they so clearly so suppose px is not uniform, right? Then you cannot assign a constant number of bits. You can in no way assign a constant number of bits. See, because I mean, suppose px is not uniform, right? Strictly not uniform, then its entropy is strictly lesser than log d. So somewhere you have to reduce your number of bit representations, right? And then how do you do it, right? Um, so people define what is called a prefix-free code. I'll just tell you this because I want to motivate one quantity. So prefix-free code. What is a prefix-free code? So suppose I have symbols, right? So let's take x, 1, 2, 3 till cardinality of x. These are my symbols. I want to assign some bit streams to these guys, such that the bit stream of one of them should not be a prefix of the other. So I'll tell you why. See, observe that x you are seeing a sequence of symbols, right? So something like this, right? So let's take for example x is x is equal to 0 to 9. Let's just take this. You're observing some sequence of symbols and so on, right? Suppose you are going to do one letter coding. Okay, what you will do, you'll assign some bit stream to 7, some bit stream to 3, some bit stream to 4, some bit stream to 5, and you keep doing this. And this bit stream goes to the other side, right? Now, suppose you were using a constant length bit stream for every symbol. Then at the receiver, you can simply block and decode. But suppose it was not a constant width bit stream. Suppose it was variable, because you have to get down to entropy means you have to use a variable length symbol, correct? How do you ensure that you know when the symbol ends? It has to be prefix free. So one of them should not be the initial part of another sequence. If one of them is not the initial part of another sequence, you know it ends, right? Clear? Otherwise, you don't know whether it's end or you're getting another symbol out, right? Clear? So a code, I will say a code for x with encoding lengths. So I'll explain this. L1, L2, L cardinality of x is prefix free if the string, if the strings b1, b2, so let me use this, okay? So b1, b11, b12, all the way until b1l1, b21, b22, b2l2, b cardinality of x1, b cardinality of x, l cardinality of x satisfy the property that none of the strings are prefix of any other string. Okay, I haven't made this very precise. It's okay. I hope you understand it. So, okay. Now the question is, for what choices, for what choices of lengths L1, L2 to Lx, does there exist a prefix free code? Right, that's what you're interested in. Does there exist a prefix free code? And out of all those, you want to choose that prefix free code for which this is small, correct? Does it make sense? So this is your average length. So choose any prefix among all the collection of, so take a prefix free code, it has a particular length distribution, right? L1 to L cardinality of X. And you're looking for that prefix free code whose average length is as small as possible, right? And you clearly know that you cannot get this to be arbitrarily small. This is at least h of px, right? Clear. So if you get arbitrarily close to this, you are awesome, right? Okay, so there's a beautiful lemma. It's a really beautiful lemma, and you should try and prove it yourself. I'll give you some hints. So this is the question, right? So for what choices of these lengths will I be able to get a prefix free code, right? It turns out there's a beautiful theorem, and the theorem is this thing. This is called Kraft's inequality. Beautiful, very small but very nice result. Kraft's inequality. Let X be a, I'll just say a source alphabet. With cardinality of F, X symbol. There exists a prefix free code of lengths L1 to L cardinality of X if and only if, so it's a very clear, sharp statement, if and only if summation X belonging to X 2 power minus Lx is less than equal to 1. Make sense? You know it? Okay. You can prove it, not difficult. The idea is very simple. You take a binary tree and you prune it. Okay, so example, I mean, I will do this with you at a later point, or I'll do it later. It's not that difficult. Example, I'll just give you an example. See, 0, 0, 1, 1, 0, maybe a 0, 1, 0, 1, 1. This is prefix free, right? Because this is not a prefix of this. This is not a prefix of this. This is not a prefix of this. Neither is this a prefix of this. Okay. One is, so because the first symbol is 0, the moment you know the first symbol is 0, you know you stop, you end. When you get the first symbol to be 1, you wait for the next symbol and then you end, right? So this is prefix free. If you look at the length, right, it's 2 power minus 1 plus 2 power minus 2 plus 2 power minus 2. So this will be exactly 1. Okay. So you choose any L1 to L cardinality of X for which 2 power minus Lx is less than equal to 1, you can get a prefix free code. That's what the theorem says. Okay. Yeah, that's also actually the proof will actually tell you how to do. So we'll meet after the class and I'll tell you how to kind of prove this. It's not that difficult. It's just pruning the binary tree. Okay. So the idea is, okay, I'll tell you because you're asking, I'll tell you. The idea is this. See, take a binary tree. I mean, you guys are all very comfortable with trees, right? See, prefix free code means if this is a code word, okay, so let's say this is 0, this is 1, this is 0, this is 1, right? if this is a code word, you should completely throw all these things out. You should throw all of this out. Okay. So by just counting how many you throw out, you can show that you will get a prefix free code. So essentially you prune the tree, you're pruning the tree, and the lengths of those prunings are essentially these length, this length of this prefix free code. I'll do the proof at a later point. It's not difficult. So you can actually come up with a clear code also. Okay. So this gives us a nice thing. So suppose we have a distribution, right? So suppose we have a set X and there's a distribution Px. Okay. Let us say Lx is the seal of log 1 by Px. So I take log 1 by Px and I take the smallest integer greater than that and I set Lx equal to that. So what is 2 power minus Lx? 2 power minus Lx is it is Px floor. I don't think it's Px floor. Let's see. It will be less than or equal to Px because you're choosing so suppose my so let's say alpha x is, so suppose I choose alpha x is 1 by Px, right? 2 power alpha x is 1 by Px. So 2 power minus alpha x is Px, right? And because Lx is greater than equal to alpha x, 2 power minus Lx will be less than equal to 2 power minus alpha x, which is less than equal to Px, right? So suppose I sum over 2 power minus Lx. So I'll essentially be getting something lesser than summation over Px, which will be less than equal to 1. Okay. So this gives you an assignment for the lengths. The moment you have a distribution Px, you just choose your Lx to be seal of log 1 by Px, and you get a candidate satisfying the Crafts inequality. Okay. What is summation Px log Px? So what is summation Px Lx in this case? It is actually summation Px seal log 1 by Px, right? So this is at most h of Px plus
Size of X.
how do you get 1? I would be interested. How do you get 1? So Tejas, just wait. Niranjan is saying is at most h of x plus 1. I think it is true, but I don't know how.
I seen the inequality. That's what I'm saying.
Huh?
I seen the inequality before, so I'm guessing it should be.
Yeah, me too. So let's see. Yeah, so that's, oh yeah, you're right. He's right. See, I mean, it's simple. We should not have thought so much. Px, so log 1 by Px plus 1, right?
Oh yeah. Screenshot. Stop sharing.
Oh, sorry. Yeah, you're right. Thanks, Srinidhi. Can you see?
Yeah. Yeah.
Okay.
Now I can see.
So it's right. So what Srinidhi is saying is right. See, this log Px, log 1 by Px is at most log 1 by Px plus 1. So now when you sum, you get h of Px plus summation Px. So which is equal to h
Yeah.
of Px plus 1. Okay. So, so you're almost within just 1 bit of the entropy. And the idea is that you just take x power some 5 or 6, then you're going to be only 1 bit above h of Px, even for five symbols. right? So suppose you take xn and you do the same thing, on pxn, right? That one will get, it will be 1 by n. You're only losing 1 by n per symbol. Okay, is that clear, Tejas?
Yeah.
Yeah. So that means we have a nice code that you don't really need to block like before. You can block with very short lengths. You can almost get down to the entropy, and this is what is called Huffman code. So if any of you are interested, you should study this Huffman code. Very nice, simple, very simple. But there are more interesting, results. Okay, now, so what do you do? Lx is log 1 by px. Okay. Now suppose you are seeing a source, you think its distribution is px, but the actual distribution is qx. Actually it is qx, you think it is px. What will you do? You will go and assign lx equal to log 1 by px, right? What is your average length? So average length is, it's actually qx. It's actually coming with distribution qx. So it's going to be qx log 1 by px. Okay. For simplicity, let us just forget the seal because I want a quantity of interest. So let's forget the seal for the moment. So I'm just going to get rid of the seal for the moment. Okay. So what do you get? You get something like this. You get qx log 1 by px. This is your average length you're seeing when you start working on the system, right? This can be written as qx log 1 by qx plus qx log qx by px. Okay, all that I've done is added and subtracted qx log qx. Okay, so this is the entropy of q. So if you knew it correctly, this was what you would be getting, but you made a mistake. So you're paying some penalty, and that penalty is this quantity, q of x log q of x by p of x. This is called the redundancy. It's also called the relative entropy. It's also called the Kullback-Leibler divergence. Okay, so I'll give a definition. So the so in quantum it's called relative entropy. In I think in statistics it's called some divergence. I don't know. There are multiple names for this because it's a quantity that is at the center of information theory, statistics, probability, whatnot. So the relative entropy or the Kullback, I might have defined it in the previous, right? Yeah, but I'm giving you some physics behind that. I mean, so you see the redundancy. This is the redundancy factor. The relative entropy Kullback-Leibler divergence, between distributions px and qx is defined as, so the divergence between px and qx is defined as px of x log px of x by qx of x. Okay. So I should state this. If so I think it is px of x being absolutely continuous with respect to qx of x. Yeah, if px of px is absolutely continuous with respect to qx. Okay, so that is whenever qx of x is 0, px of x also should be 0. Otherwise, infinity. Yeah, I think this is correct. Okay, so this is the Kullback-Leibler divergence. So we define an analogous quantity in quantum. Okay, so quantum relative entropy. This quantity will appear in the Stein's lemma also. I'm just trying to motivate it. So I'm just trying to say, okay, in the classical system, this is the redundancy if you did not know the source correctly. Okay. Okay. So one thing before I go to the quantum relative entropy is one. I'll just prove one property. This I don't know whether you've done it in the homework. So for any px comma qx distributions on x, the divergence between px and qx is always positive. Have you shown this in the homework? No. Okay, it's very simple. No.
That is the same as
Well, mutual information?
yeah, mutual
No. I mean, it is mutual information is a particular divergence. It's a divergence. So I of x colon y, which is given by h of x minus h of x given y. This is the divergence between the distribution pxy and its marginal product. Okay, but we'll show this. It's a minute. Okay, just 1 minute. Yeah, Jensen's, but I think did I defined the IT inequality right in the homework? Did I say
you asked to show I of x comma y is
non-zero?
So for that,
It's done.
I mean, you asked to show I of x comma y is non-zero, and I don't think there's any other way than showing the divergence is non-zero.
Okay. Anyway, I'll just do it. Okay, a minute. Log x. So there's one thing which you can always use. Log x is always less than equal to x minus 1 for all x. We'll just use this, and then it's very simple. So let's look at minus d of px qx. What is this? This is equal to minus. I mean, proof. I don't know. Maybe the proof is so simple. So log px of x by qx of sorry. So can I? Okay. So this is true. Px of x divided by qx of x. I'll just write this. You don't need to even write it. You can just look at my notes when it's needed. So I'll remove the minus and just write it as px of x log qx of x by px of x. So I just flipped these two guys. So this I know by this inequality, by inequality above. So this I know is less than equal to px of x times times qx of x by px of x minus 1. So which is just summation px of x minus summation qx of x minus summation px of x. So that is equal to 0. 1 minus 1. Okay. So that means I've shown minus dp minus the relative entropy is less than 0, which means plus is greater than equal to 0. So minus dpx qx is less than equal to 0. So this implies dpx qx is greater than equal to 0. Okay. So now I will define the quantum relative entropy and prove analogous thing, which is called the Klein's inequality. Okay. So definition. Suppose rho comma sigma comma rho belongs to d of h. The quantum relative entropy d of rho sigma is defined as exactly the same way. D of rho sigma is trace rho log rho minus rho log sigma. So just for you to recall, remember dpq is summation px log px minus px log qx. I just wrote it as this way so that you can relate it. Okay. So proposition. So this is Klein's inequality. We'll just prove the non-negativity of the quantum relative entropy. Proposition. for any rho sigma, the relative, how do I call it? I called it D. I don't know what was in my notes. D of rho sigma is greater than or equal to 0. Okay, so let's just prove it. It's all finite dimensional, so things are easy. I think the proof in the infinite dimensional case is not easy, and I think the clay, that's why they call it the Klein's inequality. That's my guess. In the finite dimension, it's easy maybe. Okay, the infinite dimensional proof might not be easy. But there is some recent work that makes it easier. That's what I had heard. Okay. Let's do it. It's not a big deal. I'll just use some simple notation. Alpha I xi sigma is beta I yi. Okay. So rho log rho minus rho log sigma. Not going to do the gory stuff. So alpha I log alpha I xi minus I j alpha I beta j, no, log beta j. Yeah, log beta j. Log beta j xi yj xi yj. Do you agree? Because this is essentially alpha I xi times j log beta j yj, correct? Is that okay? Okay.
Yeah.
Okay. So let's do the trace. So trace rho log rho minus rho log sigma is, I claim, alpha I log alpha I minus, I claim the following: I j alpha I log beta j mod xi yj whole square. So if you want, what you're doing is you're doing an xk, and you're summing over xk, right? So only when I equal to k, it will survive. And so you will get yj xi also at the right. Okay. Okay. Okay, let's study this. So this is so observe the following. So let me call theta ij equal to xi yj whole square. Okay, just for simplicity, just for less clutter. So alpha I log alpha I minus I alpha I, and there I have a j theta ij log beta j. Observe the following. So suppose I sum over j of theta ij, what do I get? Claim this is mod xi whole square, because I'm summing over j, right? So I sum over all the coefficients of xi in the basis yj. So this is 1, correct? Because when I sum here, right, I'm summing all the coefficients of the vector xi in the basis yj square, sum square. So it's 1. Okay. So which means so what is this? This is like this is like 0.2 log beta 1 plus 0.4 log beta 2 plus 0.6 not 0.4 log beta 3, right? So when I sum over theta, when I sum over j, I get 1. So it is like, so what am I doing? I have this log function, right? And I'm looking at the chord. So this is your beta 1, this is your beta 2. So this is 0.4 log beta 1 plus 0.6 log beta 2, right? So I mean, just for clarity, so this is log beta 1, this is log beta 2, and I'm taking a convex combination of the two, and this is the chord, this is the point. This point is log 0.4 beta 1 plus 0.6 beta 2, right? So the curve lies above the chord on the concave thing. So with this, I'm going to pull this diagram out a little bit the other side. I'm going to just minimize this. So I claim, so whenever, so this is just concavity, I'm just writing this, whenever summation gamma I equal to 1, then, and gamma i's are all positive, then summation gamma I log beta I is strictly lesser than log summation gamma I beta I. This is just the concavity of the log. So which means that I can go from here to say that this is at least I alpha I log alpha I minus I subtract a larger quantity. So it's I alpha I log summation over j theta I j beta j. Is that okay? So I just pull the summation inside by concavity of the log, and I increase the term, and hence I decrease the value. Is that okay? Now what? Tejas, so far okay?
Yeah.
Okay. Now what?
Now I can just take the alpha common.
Now the idea is the following. I mean, it's very simple now. So let us define gamma I to be summation j theta I j beta j. Okay. Observe. So clearly gamma I is greater than or equal to 0. Right? Because beta j, remember what the beta j's are. Beta j's are the eigenvalues of sigma. So all the betas are positive. All the theta ij's are also positive. Suppose I sum over gamma I, what do I get? I j theta ij beta j. So you can show, similarly, you can show theta ij when I sum over I is also 1, because this is summation over I mod xi yj. So whether I sum it over j or I sum it over I, I'll get 1. Okay. So, so I'm going to get j beta j, because I've summed the I, I've summed the theta ij over I and I get 1. So this is also 1. So gamma is some other distribution, that's all. It's some other rotated distribution. So what I get, what have I got? I have got this to be the divergence between the vectors alpha 1 to alpha d and the vector gamma 1 through gamma d, where gamma I is defined as above. J theta ij beta j, and theta ij is defined as mod xi yj. So I have shown that. So this is the divergence, and I know the divergence of between any two probability distributions greater than or equal to 0. So that's why I did the previous step. Okay, I use the redundant. I mean, I just motivated through the redundancy. The redundancy is always positive. You cannot do better if you don't know the distribution. If you wrongly estimate the distribution, obviously you have to pay more. That's what the divergence greater than or equal to 0 shows. And I reduce the quantum relative entropy, the positivity of the quantum relative entropy also to the case of the divergence of two distributions being positive. Okay, clear? So all that I'm saying is the relative entropy is always positive, and the Klein's inequality is using the concavity of the log and the divergence of two distributions to be, the classical divergence to be greater than or equal to 0, to just come up with some algebra and show it. Okay, is that okay, Tejas?
Yeah.
Okay, great. So that's the Klein's inequality, and now we will use this to prove a lot of properties of the von Neumann entropy. Okay, so recall the von Neumann entropy is essentially minus trace of rho log rho. Now I'll state some properties of the von Neumann entropy. So theorem, proposition. Some of it are straightforward, but I'll just state it. Proposition 1. So the von Neumann entropy is sandwiched between 0 and log dimension of the Hilbert space of D. That's straightforward. That follows from our first thing. Second, okay, there's some interesting things here. Some actually remarkable differences between the classical and the quantum, and so we'll come to that. Suppose my joint state is pure. Okay, suppose my joint state is pure, then the entropies in each of the components are identical. Okay, very interesting. What is S of rho AB? I mean, just as a aside, I'll write this in blue. What is S of rho AB? Huh? Yeah, but what is the von Neumann entropy of density operator? No, von Neumann entropy of any density operator.
Trace of rho log.
Yeah,
rho.
that's the Shannon entropy of the eigenvalues, right? What are the eigenvalues of rho AB? 1 and zeros, right? So what is the Shannon entropy of that? Shannon entropy of a singular distribution? 0. So it is 0. Tejas, you're okay with this?
Yeah.
Okay, because the eigenvalues of rho AB are 1, 0, 0, 0. The Shannon entropy of that vector is 0. But its components, I don't claim has 0 entropy, but I claim that the components have equal entropy. Observe, remember in your classical, you showed this, right? H of x comma y is less than equal to h of x plus h of y. And you got distribution. I mean, if h of xy is 0, what can you say about h of x? Huh? He's saying they're both 0. Because remember, h of xy, right? H of xy is h of x plus h of y given x, correct? And everything is positive, non-negative, sorry, non-negative. So if this is 0, then every guy should be 0, right? So I can also write this as h of y plus h of x given y. So the way you should read this chain rule, this is called chain rule, okay? The way you should read it is the uncertainty in xy is the uncertainty in x plus the uncertainty in y given x. So somebody gives you x, how much uncertainty you have in y, okay? So if h of xy is 0, everything is 0 because xy itself is 0. Okay, so you know what is x and y. How can there be any uncertainty in x? Because if you know x comma y, you know x, right? But here, your composite system is joint system is singular, but the individual systems are uncertain, right? And that's understandable, right? That comes from your entanglement, right? Okay, so we'll show this. So at least can you how do you show this?
Taking trace of A is equal to trace of B.
Okay, trace of A, trace of B is trace of AB. That's
Yeah.
okay. Okay. Okay, let me state all the things and then maybe we'll come to each one of them. 3. Suppose row 1, row 2 to row k have orthogonal support. So in other words, if I do the spectral decomposition, if I take any two any two spaces on which they project, they are orthogonal. Okay. And P1, P2 to Pk are sum to 1 or non-negative summing to 1. Well, I should just say and P2 suppose I just say is a distribution, is a PMF, probability mass function. Then if I look at the mixture, I can look at the mixture, right? The entropy of the mixture has two components. First, give me the Shannon entropy of the vector P plus the convex combination of the entropies of these von Neumann entropies. Okay. We'll prove this, not a big deal, just calculation. So so the way to read this, I'll tell you the physical way to kind of read this equation. So if somebody has to tell me about this mixture, they can first tell me the index. Okay, so let me see, how do I Okay, I will recall an interpretation. So the way I kind of look at this is that you first tell me which first tell me which index k is your system. So for that you need so many classical Shannon bits, classical random bits, and with with probability pk, you have to then tell me the von Neumann entropy of the density operator to cook up this summation pk or okay. Okay, I will actually interpret this slightly better next time. I had a way to kind of write this thing. I think I'm not able to recollect that. Okay, I will do one more last thing and then we'll come to the proofs. Or maybe, okay, I'll just state one more last thing and we'll come to the proofs. Suppose, so in the previous lemma, I need rho 1 to rho k to have orthogonal support, but now I'll do something slightly trivial extension of that. Suppose rho 1 to rho k are in D of H. P1 to Pk is a PMF. Then and Vi belonging to H, 1I to K are orthonormal. So I have a bunch of density operators. I have a distribution with which I can mix them, and I have a bunch of orthonormal states. So then if I look at this, it's a trivial restatement of the previous lemma. So if I look at Pk, Vk tensor rho k, then it is essentially the same as the previous. H of P plus summation Pk s of rho k. Okay, so we'll prove all of this one by one. But the interesting thing is that first thing is trivial. I think first thing is straightforward. Right, first statement is straight. Huh? Yeah, please. Yeah, sure. Here it is. Orthonormal, not necessarily basis. I think there is one more statement I forgot. Let's see. No, that's not. That's all. Okay, let's prove it. So the interesting thing, so one is straightforward, right? One is straightforward. Done. Just the Shannon entropy of the eigenvalues, and this you just apply that. Second one is interesting. So let's do the second one. So proof of second one. So the proof is very simple. See, you have rho AB, right? This is the vector V, the rank 1 operator V living on H8 tensor HB, right? What I will do, I will use the Schmidt decomposition. What does the Schmidt decomposition say? So given any vector V, given any vector V in H8 tensor HB, there exists orthonormal basis EI 1I to D1 inside HA and ONB sorry, Fj 1jd2 inside HB such that vector V can be written as summation lambda I ei tensor Fi I equal to 1 to D, where the lambda i's are all positive and D is something less than the min of D1 comma D2, right? Correct? This is the Schmidt decomposition. So I can write it as something sitting in the middle, right? So I can do this for any vector V. The choice of the EIs and the FIs depend on the V and the lambda i's. It's just you did this in the homework. So what is the vector? What is the rank one operator? The rank one operator is essentially ij lambda I lambda j ei ej tensor Fi Fj, right? What is rho A? When I trace on the second component, I am going to get summation lambda I ei, right? When I trace over the first component, I get summation lambda j Fj Fj. I mean, I'm just using different indices, but they're essentially the same. Correct? So the vector of eigenvalues are identical. So S of rho A equal to S of rho B by remark 2. The vector of eigenvalues are identical. Okay? Clear? So the uncertainty in each component is identical. Okay. The third one is trivial. Third and fourth are trivial. Okay, I'm not almost going to do it. So 3. So rho 1 to rho k have orthonormal support, right? Have orthonormal support. It's just notation really, this one. So you can show. So let's do this. So summation pk rho k, I claim has a spectral decomposition. So let me do rho j. So let's say rho j is lambda j a eja eja a equal to 1 to dj. Okay, so I claim summation pk rho k is k a equal to 1 to dk pk lambda k a e k a e k a. Okay, so these are all orthonormal. All the EKs are orthonormal because they have orthonormal support. Is that okay? So you are going to get the Shannon entropy of this big vector pk lambda ka k k is just notation, k in capital K, 1 less than a less than dk for all k. I mean, you have to understand this. It's just notation. So you're going to get something like this: minus pk lambda ka log 1 by pk lambda ka. Okay, I'm not going to do all this. Just straightforward calculation. This is homework. And you will just show that it is essentially h of pk plus summation pk s of rho k, because here you are going to get summation lambda ka log 1 by lambda ka. Okay, just split this log into 2 parts and you do it. That's all. You just split it as log 1 by pk plus log 1 by lambda ka In the first part, you will sum over A and you will get H of P. In the second part, you will sum over K and you're going to get PK S of rho K. Okay, straightforward. The third part, the fourth part is also just straightforward extension. All that you have to do is this has orthonormal support. Okay, so call this sigma K. Observe that sigma 1 to sigma K have orthonormal support. That's all. Have orthonormal support. Because you're tagging it with this VK. Yeah, you're not projecting, you're tagging it with this VK. Yeah, you're tensoring it with this VK. And then the eigenvalues of VK tensor rho K is same as the eigenvalues of rho K. So everything goes through. Okay. Clear? Just the exercise, a very simple thing. Okay, I'll do two. It's already 9 o'clock. So another just 4-5 minutes and then we'll go because we have to go for dinner. Okay. Okay, so I will do. Okay, let's see. There's actually a good point to stop. There are a few 2-3 things and then we'll be done, but I'll not finish everything. I'll just do one. So I'll just do one last thing. So suppose PK 1K K is a complete orthonormal complete projective measurement. So what do I mean? Complete projective measurement. That is PK equal to PK dagger equal to PK squared. So they're all projectors. And summation PK is identity. That's what I mean. Just a projective measurement, complete projective measurement. Yeah. So suppose you make a measurement on rho. Okay, so you make this measurement on rho and you don't tell me the outcome. You make the measurement and you don't tell us the outcome. What is the post measurement state? What is the post measurement state?
Summation of PK row, PK dagger, trace of, no, the trace cancels it.
See, when you make the measurement, right? When you make any measurement, right? So suppose you have MK. So let's just take. So suppose you take any measurement MK, your post measurement state is this tensor KK. So you have a component, you have a quantum component and you have a classical component, right? If you don't tell me the classical component, that means you're tracing out, right? Tracing out on the classical component, which means that you get this. Okay, when you trace over KK, you're going to get 1 and you sum over all that. Okay. So this is your post measurement quantum state when the classical outcome is not revealed. In the case of the projective measurement, you're going to get PK rho PK. Okay, PK dagger is PK. So this is what you get. Okay. So this is the post measurement state. How does the entropy of the post measurement state compare with the pre measurement state? What's your guess? So the entropy is like the uncertainty. You made the measurement. Let's take an example.
I mean, the author will like to use something from before, but that's the probability.
So let's do an example. Okay, let's do this. Suppose Tejas, your question is clear, Tejas?
Yeah, questions.
Okay, let's do an example. Let's take our rho to be this state. Okay, let's choose our P0 to be this and P1 to be this. Okay. What is S row? S of row?
0.
0. What is summation pk row pk? So what is p0 row p0 plus p1 row p1?
0, 0. That will
So
be
this guy is 1 by root 2 0 0. Sorry, 0 plus 1 by root. So let's go step by step so that we don't make mistake. So plus this is 1 by root 1 by 2 0 0 plus 1 by 2 0 1 plus 1 by 2 1 0 plus 1 by 2 1 1. Correct? Am I right? So what is P0 row P0? P0 row P0 is only this term will come. So 1 by 2 0 0. What is P0 row P1? I'll get 1 by 2 1 1. So the post measurement state is maximally mixed, right? So what is the entropy of that? So log 2.
1.
1. So what happens? So summation pk row pk, the entropy of that seems to be greater than the entropy of the state, right? So this is the theorem. So just proposition. Suppose pk is a projective measurement for any row density operator. We have that the measurement when the outcome is not revealed has a higher uncertainty. Okay. I think we'll go, right? Maybe, okay, I'll just complete this proof and we'll go very quickly. The proof is a very bad proof, but let's, how do you want to show this? So whenever you see this kind of a thing, what you should, I want to just indicate this. When you have this kind of a thing, what do you try? Which one?
The S of summation of the constant
Oh, that may be hard.
and H of S is the positive term, I mean, this side is greater than that.
Oh, so you will use that, huh? Is that do they have orthogonal support? Suppose I say sigma k. Okay, you're saying sigma, they have orthogonal support. They have orthogonal support. Yeah. Yeah.
Because each peak is orthogonal.
Yeah. So you're saying I'll call pk row pk as that. So, but there you are saying some
Yeah,
S
there's
of
some probability distribution
Ah.
there, which I will have to take as like a identity, like equally distributed or something in this case. Yeah, like that probability distribution is where I'm getting this.
yeah. It's a good idea. It's a good idea. Huh?
You could just calculate.
You can't actually. This proof is very tricky proof. A bunch of tricks. Okay. I want to get a better proof. I was not able to get a better proof. So maybe you should try. Okay, let's stop and then let's try it out. See if you can get a better proof. You might be able to get a better proof. And there are only 2 or 3 more things, and then with that we can go to the coding part. Question, Tejas, questions?
No, it's fine.
Okay, so I will
Yeah.
record this. I will post this. I'll send the notes also, and then we'll continue. We'll continue with the next class. We'll finish. We'll actually finish whatever we require now. I started a little late, so I think we can't go too long. That's the problem. Okay, I will. Is that a fine, Tejas?
Yeah, yeah, sure.
Okay, cool.
Yeah.
See you then.
Okay. Yeah, bye.
What happens to the recording if the recording doesn't work, guys?
Start saving.
See, it's not. It does to the cloud, right?
You just download it now.
See, it says, oh, okay. It's still recording, so I should stop it now, right? And when I stop it, it'll start saving, right? Hopefully it does that.
So that like
Stop. You will receive an email notification when the cloud reading is ready.